In this video here, we're going to take a look at boundary conditions. So you should be familiar with the idea of using boundary conditions to find particular solutions to first order differential equations. Now for this video here, we're now going to look at how we can find a particular solution to a second order differential equation. And because we have two arbitrary constants, we will need two boundary conditions to determine the complete particular solution. So let's just have a look then at a practice question to help demonstrate this concept of boundary conditions. So let's begin then with this one practice question here for boundary conditions. So we'll start off with part A then, which asks us to find the general solution to this given differential equation here. So to get us started then with part A here, the first thing that we need to find is the auxiliary equation. Let's just write this down here. So the auxiliary equation will be given as follows. So the auxiliary equation. So this will simply be m squared plus 5m plus 6 is equal to 0. Okay, so we get m squared plus 5m plus 6 is equal to 0. Okay, so now if we attempt to factorize this here, well, what we obtain then is m plus 3 and m plus 2. Okay, and that's equal to 0. And in that case then, we can see that our two solutions for m here will be m equals minus 2 and m equals minus 3 here. Okay, so in that case then, what we can see here is the complementary function, which I'll abbreviate to c dot f here, is given as follows. So it's going to be y equals, so we get ae to the minus 2x here, plus b to the minus 3x here. Okay, so this here then is our complementary function. So what I've got here then is f of x. So f of x is equal to 12e to the x then. So 12e to the x here. So in that case, then my particular integral here will be of the form lambda e to the x. Okay, so our particular integral, which I'll shorten to p dot I here, our particular integral will be of the form lambda e to the x here. Okay, and let me just change that to an equals actually. So our particular integral here is lambda e to the power of x. Okay, so in that case then, if we differentiate this here, dy by dx is also lambda e to the x. And the same is true for the second derivative here. Okay, so the second derivative of y will also give us lambda e to the power of x here. Okay, so now let's substitute this here then into this equation. Let's call this equation 1 here. Okay, so sub into equation 1. Okay, so sub into equation 1 here. So in that case, then we have the second derivative. So that's lambda e to the x here. We get lambda e to the x. We have 5 lots of the derivative here. So 5 lots of dy by dx. That's 5 lots of lambda e to the x here. So I get 5 lambda e to the x. And then what else do we have here? Well, I've got 6y. So y here is lambda e to the x. So I get 6 lots of lambda e to the x here. So 6 lambda e to the x. And that's equal to 12e to the x here. Okay. If we simplify the left-hand side here, what we get then is 12 lambda. We get 12 lambda e to the x is equal to 12e to the x. Okay. And in that case, then what we can see here is that lambda is equal to 1. Okay. So in that case, our particular integral here is lambda equals 1. So we just get 1 times e to the x, which is just e to the x here. Okay, so I'll make a note here. The particular integral then is e to the x. Okay, so what we can do now is note the general solution here. So therefore, the general solution So for the general solution here, this is given as follows. So it's y is equal to, so don't forget then the general solution is the complementary function plus the particular integral. Okay, we'll get ae to the minus 2x plus b to the minus 3x, and then plus the particular integral here, which is e to the x. Okay, so plus e to the x there, and there we have it. So this here then is the general solution, and that gives us the solution to part A. Now for part B then, it's a bit of a follow-on, right? And we do need a little bit of room here. So let me just quickly clear the screen. What I would recommend, if you haven't already done it, is just write down the general solution here, because obviously we're going to need this general solution to find the particular solution which satisfies this condition here. Okay, so let's just quickly clear the screen then. So we've cleared the screen now, so let's have a go then at answering part B here. And just for reference, I've also included the general solution here, just to help us answer part B. So for part B then it says, hence find the particular solution that satisfies y equals 1 and dy by dx equals 0 when x equals 0 here. So to start off with then, let's just note here that when x equals 0, so when x equals 0, y is equal to 1. So all I need to do here is substitute this value of x and this value of y into our general solution. So in that case, we get 1 is equal to, so we get a times e to the 0, so that's just a times 1, which is a. Doing the same here then for b, we get b times e to the 0, so that's just b times 1, which is just b. And then we get e to the 0, which is just 1. Okay, if we simplify this here then, we get a plus b is equal to 0. And in that case then, we can just write this here as a is equal to minus b. Okay. Now let's do the same here then for the second condition. So dy by dx is equal to 0 when x equals 0. So let's just note that here. So when x equals 0, dy by dx is also equal to 0. So what I need to do here then is differentiate my general solution, right? That would give us dy by dx. So in that case then, we obtain dy by dx, which is equal to, so nice and straightforward here, right? We get minus 2a e to the minus 2x. So minus 2a e to the minus 2x. We then have b to the minus 3x. If we differentiate this here, then with respect to x, we get minus 3b e to the minus 3x. So minus 3b e to the minus 3x. And then finally, e to the x just differentiates to give us e to the x again. So plus e to the x there. So all we need to do now is use this boundary condition here. So in that case, then we have 0 is equal to, we get minus 2a here, minus 3b, plus 1, like so. Okay. So in that case, then, what I'm going to do here is use this equation and this equation. Let's call this equation 2. What we can do now is just solve these simultaneously, right? They're just simultaneous equations. So it's up to you how you go about solving this, whether you just use substitution or elimination, completely up to you. But in that case here, given that I've got minus 3b minus 2a plus 1 equals 0, and we know that a is equal to minus b here, all I'm actually going to do is just replace a with minus b. Okay, so I get minus 2 lots of minus b, because a is equal to minus b here. Minus 3b is equal to minus 1, right? Just taking 1 off both sides here. So in that case then, minus 2 times minus b, that's just the same as 2 times b, just becomes positive. So I get 2b minus 3b is equal to minus 1 here. Okay, so we get minus b is equal to minus 1. And in that case then, just solving for b here, we obtain that b is equal to 1. Okay, and in that case then, if a is equal to minus b, in that case, a is equal to minus 1, right? So nice and straightforward there. We've obtained a is equal to minus 1 and b is equal to 1 here. But we're not done here. So don't forget we want the particular solution. All we found here is a and b. So what we need to do now is just rewrite the general solution with this value of a and this value of b. Okay. In that case, then, the particular solution here, let's just write this down. So the particular solution is given as follows. We get y equals, so a is minus 1, we get minus e to the minus 2x. We then have b to the minus 3x, so b is equal to 1. I get plus e to the minus 3x, plus e to the minus 3x here. And then finally we have e to the x here. Okay, so plus e to the x there. And there we have it. So this here then is our solution for part B. That's our particular solution there. And there we have it. So that gives us the solution to this one question here for this video. And that actually brings the end then of this video here on boundary conditions.